Now we're going to take a look at something that you might have seen back in Math 210, and that is something called relations. And we're going to make a particular focus on something called equivalence relations. So first, we're going to describe some different models of relations and illustrate them with some examples. We're going to see how different models give us different understandings of how a relation works. And then we're going to see how different models lead to different types of relations that we're going to be studying. So here is the official, precise mathematical definition of what a relation is, and then we'll get into the models. So if you have two sets A and B, we say a relation from A to B is just a set of ordered pairs in the Cartesian product A cross B. So we can think of this relation in a variety of ways, and this is just for communication. If we literally have an ordered pair A comma B in the relation, that's just an ordered pair, we say that A is related to B under the relation R. We also sometimes write A R B to mean the statement A is related to B under R. So an ordered pair in R is just saying that two things are related, and if I say ARB, that is a statement that means the two things are related. Just two ways of saying the same thing. So that's equivalent to saying that the ordered pair AB is an R. All right, so we have some models that can help us understand these relations. So the model that is the most general, I think, is, I like to call it the social media model. So the relation R can be thought of as expressing some kind of social media relationships, like on Instagram or Twitter, something like that, where we say A or B can be thought of as A follows B. So if A follows B, it is not necessarily true that B follows A. That is certainly the same in the social media relations as well. So if you have the less than or equal to relation, let's see. So here A related to B means A is less than or equal to B. Since 2 is related to 5, 2 is less than or equal to 5, we could think of it as saying 2 follows 5. And in fact, all smaller numbers follow our larger numbers, or numbers that are equal as well, but not the other way around. So in terms of ordered pairs, we can say that the ordered pair 2 comma 5 is in the relation R. However, just note that 5, 2 is not in the relation R, even though it includes the same numbers, because it is not true that 5 is less than or equal to 2. All right, so another model for relations, this one always works in a very visual way. It's called the directed graph model. So if we have a relation R between the sets A and B, if we have two elements A and B that are related, so A is related to B under the relation R, we can express this as A with an arrow pointing to B. And so this can give us kind of a global look at what the relationships are under the relation in the following way. So let's say I have a relation that's just a bunch of ordered pairs. So 1 is related to 5, 2 is related to 8, 3 is related to 7, 1 is related to 2, and 3 is related to 5. How could we express this visually? Well, here's what the directed graph would look like. So here's 1 pointing to 5, right? So the first ordered pair is 1, 5. So we have 1 pointing to 5. The next one is 2, 8. So that means 2 points to 8. And just to show you that the arrows don't have to go left to right, for 3, 7, I can put 3 on top. It's pointing down at 7. It's just that the first element in the ordered pair has to point at the second element in the ordered pair. And then we get, with 1, 2, we get some elements that are already in our picture. We don't have to redraw 1 and 2 and draw an arrow between them. We can just draw an arrow between the existing representations of 1 and 2. And same with 3 and 5. We point an arrow from 3 to 5. So that's what the relation looks like as a directed graph. So here's a model that is really useful, but not for all relations, only for certain relations. And that is, I call it the team model. So this is actually a model for a relation called an equivalence relation. And so an equivalence relation can be thought of as some kind of team relation where when I say A or B, that means A is on the same team as B. So in this case, we have elements that are put into teams. So team relations behave a little bit differently than relations in general. First of all, if you have teams, every person who's on a team is on the same team as themselves. And in fact, that also tells us that the two sets that are relating things have to be the same set as well. So that says that A is related to A for all people A. So if A happens to be on the same team as B, it follows very directly that B has to be on the same team as A. If we're looking at that in the language of relations, that says if A is related to B, if A are B, then B is related to A, B are A. And finally, if A is on the same team as B, and if B is on the same team as C, well, then it's going to logically follow that A and C have to also be on the same team. So that means A is on the same team as C. In the language of relations, that tells us that if A is related to B and if B is related to C, then A is related to C. So that actually inspires some very more general properties that are inspired by the team relation. So if A is a set and R is a relation on the set A, and notice that it's not a relation from one set to the other set, it's a relation between elements of the same set A. We say that the relation R is reflexive if A is related to A for all A in the set. We say that R is symmetric if whenever A is related to B, then it also follows that B is related to A. And we say that R is transitive if whenever A is related to B and B is related to C, then it follows that A is related to C. So I'm going to give you a visual representation using the directed graph model. And since these are pretty much all stated as if-then statements, I'm going to have two types of arrows. One are the solid arrows, which indicate what we're assuming in the definition. And the other is going to be the dashed arrows, which are conclusions. So for our reflexive property, well, we're not assuming any arrows exist. However, we are making the assumption that our little a is a subset in A. So that's the kind of that's our starting point. Not with any arrows, but with just A. And then the conclusion is A is related to A, which means that A points at itself. So I put a dashed arrow between A and itself to say that whatever A is, it points at itself because it's related to itself. So for the symmetric, we assume that A is related to B, and if A is related to B, then it follows that B is related to A, so we've got a dashed arrow back to from B to A. And for transitive, we have two assumptions. First, that A is pointing to B, that's our first solid arrow. Then we're assuming that B is related to C, that's our second solid arrow. And then our conclusion is that A is related to C, that's our dashed arrow. So now that we have those three properties, we're ready to define equivalence relations. And all the equivalence relation is, well, let A be a set, let R be a relation on A, then R is an equivalence relation if it satisfies all three of those properties that we were talking about. It satisfies the reflexive property, and it satisfies the symmetric property, and it satisfies the transitive property. All right, so now it looks like you're probably ready to work on some of these equivalence relation type questions. I have a set of in-class activities called More Relations included with this video.